Okay, so let's get started. Few of you asked me, what do we study from Dr. Labuza's lectures?
That's fair.
So the first lecture he gave on moisture content, all the different methods of how to determine moisture. I would like you to focus mainly on those that you did in the lab. So the oven methods, the microwave, the Carl Fisher. So John, are you with us? Okay. So these methods that we focused on in the lab, and you want to know what alternative methods are out there, but I won't be asking about principles of alternative methods, but at least you need to know, have an idea. In terms of water activity and isotherms, also I want you to know everything that is related directly to the lab. What water activity means, why do we measure it, how does it relate to moisture content, and the generation of linear, BET, and gap isotherms, how are they different, and the use of an isotherm, why is it important. So these are pretty much what I'd like you to know. And of course the story when he was arrested, that's almost arrested.
So what about the rat method?
Yeah, the rat method is important? No. Well, okay. What's that?
Chelsea committed it. Oh, yeah.
Just once?
I hit the neighbor's mailbox that I kept driving to school. I was only 16 and I had
Okay, and you also need to know his the license plate.
No.
Okay, so proximate analysis. This is actually an introduction that encompasses moisture, but I want to talk about what proximate analysis mean, and from now on the lectures are going to be really more practical than what we have covered in the past. We covered chromatography, spectroscopy, all cool methodologies, and from now on, how do we actually measure things, and how do we apply chromatography, for example, for different components, how do we apply spectroscopy, and all of that. But before we go into characterization and analysis of different components, proximate analysis is a big component of food analysis, and it really encompasses what? When you hear proximate analysis, what do you get out of that? Yeah, back in the habit of talking to me. Okay, so what does proximate analysis mean to you when you hear this term? What does it encompass?
Analyzing something we're not certain about?
Okay, we're not certain about, but what are we analyzing? What do we approximate?
Like for the basic, generally count components, so like protein, carbs, fat.
Macromolecules, macro components of food. So your basic ones are your moisture, your protein, your fat, your ASHE, and also your carbohydrate. So 5 major components of food that you learn about in food chemistry, you learn about even if you take nutrition, you learn about all these macro components of food. So proximate analysis is approximating the major components of food. So this does not include vitamin, this does not include color, this does not include flavor, this does not include micro components. It's the macro components of food. Okay. And like Erin said, that is absolutely correct. It's proximate. So all of the methods are really crude. We call them crude protein content, crude moisture content, crude ASHE content, because you are approximating the amount, not the exact measure. For example, in protein, we determine nitrogen and we convert it to total protein, and not all nitrogen in your food is from protein. You have nitrogen in vitamins, you have nitrogen in urea, you have nitrogen in free amino acids, and free amino acids are not protein. Okay, so that's why it's approximate of crude analysis of different components. Okay, so all of these major components, the moisture, ASHE, fat, protein, and total carbohydrate, if you sum them all up, they would approximate to 100%. So these are the major components of food, and when you sum up the percentages of all of them, it should add up to 100% of the major components in food. Okay? So in nutritional facts, which ones of these components are reported? Okay, you can raise your hand, Yafar. Go ahead. Fat, carbs, and what? Protein. That is absolutely correct. So this is, by the way, the new nutrition label. The handouts that you have had the old one. So basically, you see here, you have the total fat. Now these are subcomponents of fat. They get analyzed when we cover fat characterization chapter. We're going to talk about these. Okay, cholesterol is also a subcomponent, but the major ones, you have fat, you have carbohydrate, and you have protein. Okay? Good. So, but all analyses are required for nutrition label. In order to generate a nutrition label, we have to analyze all of these. Why? Does anybody know? Andy?
Isn't it because carbohydrate is basically a little leftover, so we analyze all of them because we don't have a good carbohydrate method?
Andy got it. So carbohydrate usually is not determined by an experiment for nutritional evaluation or for nutritional labeling. It's basically you determine percent moisture, ash, fat, and protein, and you subtract the sum of that from 100, and you get total carbohydrates. Some of you would go, why? You can determine dietary fiber alone, starch alone, sugar alone, and combine all of that, and you get the percent total carbohydrate. Well, here's why we don't do that. I mean, that would be the accurate way of doing it, but here's why we don't do it. So you have to think about the food components as a constituents of a pie chart. So you will have the ash, you will have the moisture, you will have the fat, you have the protein, and then you have the carbohydrate. So ash, fat, protein, protein can be protein, moisture, and this here is your carbohydrate. If you go ahead and analyze these by crude methods, and then you go and analyze carbohydrate by doing all of the different methods, starch, dietary fiber, and sugar, what could happen is you end up over 100%.
Yep.
You'll end up probably 105. Or you might end up as 98%. Because these are crude. And if you go ahead and do accurate determination of different components, then you won't end up with a pie of all of them adding up to 100. So we go ahead and do the carbohydrate by subtraction, and that would be a crude approximation of your total carbohydrate. Okay? All right, so in order to use the values for nutrition label, we already know by now that you have to use official methods of analysis. And that's, for example, for different food products, moisture content is determined by official methods of analysis using oven methods, either the vacuum oven or the forced draft oven. Ash, the official one is the dry ashing. Some of you have done that today in lab, where you put your sample in a muffle furnace and ash your sample or burn off all your organic matter, and that's what we're going to talk about today, mostly the ash analysis. Fat, official methods are Soxhlet and Mojina. They're very common for different food ingredients. However, notice this red here. For nutrition labeling, recently, I don't know how recently, but recently, they determined the definition of lipids. Does anybody know what the definition of lipid is? What is lipid? hard to define it, isn't it?
It's a, it's a product that's a result of either bioester or dehydration, and another compound, I forget.
Okay, you're going too technical and too deep here. What's the yeah.
Not easily soluble in water?
Yeah, non-soluble in water. Soluble in organic matter. Everything in food that is not soluble in water, which is a very vague definition of lipid. And lipid components can be your typical triglycerides, you have your cholesterol, you have phospholipids, you have mono and diglyceride. You have so many different components, but they're all categorized as lipid. So based on the definition of being vague, then FDA came in and said, okay, let's define the amount of fats on your nutrition label based on the fatty acid content. They determine fatty acid content and convert all of it to triglyceride. Although fatty acids are probably coming from phospholipids, from cholesterol, they're coming from mono and diglycerides, but they take the fatty acid composition and they convert it and report it as triglycerides. So for that, to generalize and to get that definition, the efficient method for determining total fat is your very own GC FAME method that you've done in the lab, but definitely what you've done in the lab is semi-quantitative. There is the full-blown quantitative method where you have standards for all fatty acids from C4 to C24, and you generate a standard curve for each one of them, and you have an internal standard, and you get the composition, complete composition of fatty acids and quantity, and all of them are converted to triglyceride. And that's how you get your total fat. Okay, protein, simpler. It's the two official methods that are commonly used for all types of food are the Dumas method based on nitrogen combustion and the Kaldal method, which is a highly complicated procedure, but it's the golden standard for protein analysis. And we will talk about that actually on Friday, where I'll be gone in Chicago, and Chelsea is going to give that lecture. Okay. And then total carbohydrate, after you obtain these, you subtract from 100 and you get your total carbohydrate. Well, that's basically summing it up to get the equation where you get total carbohydrate. All right, so that's your proximate, and so far you've studied moisture analysis. So now we're going to talk about ASHE. On Wednesday we'll talk about fat, on Friday protein, and then that would be it for proximate analysis. Okay, what's the definition of ASHE? Nora?
Inorganic material left behind after decomposing the organic material.
That is absolutely correct. But here's some animation. So basically, you get your sample, you burn it off at really high temperature, and then your organic matter will evaporate or get oxidized and actually evaporates in the form of carbon dioxide, nitrogen oxide, or sulfur dioxide, and H2O. So they're all leave in that matter, and what's left behind is your inorganic matter. And if you see here, this is ideal. What you want to see is really a white ash. If you don't see a white ash, that means some of your carbon matter did not oxidize, did not burn off. So when that happens, when you have a sample with a lot of dark substance still left in it, normally what you would do is you would take it out and you would add some nitric acid. The nitric acid, it can digest the sample even more. You put it on a hot plate, you evaporate the acid, and then you put it back to ash for a couple of hours, additional couple of hours. If you don't do that and you have a lot of dark carbonic substances still left, then your total ash will be overestimated. So you will overestimate the inorganic matter in your sample. But we need to be careful about doing that, because if you put it for over time in the muffle furnace, what can happen is some of your volatile minerals will evaporate. And with that, you get underestimation. So, but again, that's why we go back to the approximate when we say crude, because you cannot really get the perfect number for ash. You're always either overestimating or underestimating when you're determining ash content. So why is it important to determine ash content? Why is it relevant to us? Yes? We just said, yes, you're correct. We just said that we need to analyze all components in order to report the total carbohydrate on our package. That is one. What else? Where did you use ash analysis earlier this semester? Yes, Josie?
To get minerals separated so you can do
Exactly, for mineral analysis. So it's important to ash your samples to do mineral analysis. So, okay, so this is the old label. I should find another cartoon for that. But anyway, it's part of the proximate analysis. Are you familiar with Popeye?
Yeah.
It's a cute cartoon. I used to watch it when I was little. But you know how he gets his strength, right? From eating spinach. It's high in iron. Okay, so it's a preparation step for specific analysis. Iron in particular because it is needed on the nutrition label, along with obviously sodium and now potassium and calcium. So sample preparation. Some of you have cheese as a sample. Oftentimes when you have a product that is high in moisture like cheese, you really need to pre-dry it. Otherwise, if there's a lot of moisture, then when you put it at high temperature, really high temperature, like 500 degrees C, what's going to happen is the water starts to boil off. And by boiling off, you're going to get splattering. And your sample is going to splatter out of your crucible, and then you'll have underestimation of your ash. Obviously, you need to mill and grind your sample. For proximate analysis, all except fat, you need to have a mesh number of 20. For fat, you need a mesh number of 40, if you remember from your chapter 5 of sample preparation. So the sample needs to have high surface area, so you need to, for proper evaporation and oxidation of the components, so you need to grind your sample. You cannot put chunks in there. But one thing you want to watch out, especially if you want to determine mineral content, is the whatever you use to grind your sample. So if you're using a mill, a small mill, and if it's made of metal, you might contaminate your sample with the metallic component of that mill. So gotta watch out for that, for contamination, keep that in mind. Oftentimes you need to extract the fat, which we didn't do for the cheese analysis. We did not extract the fat prior to ashing, but there is a step you can do to avoid problem with the fat. So theoretically and ideally, you extract the fat to avoid any smoking of your sample. But other ways to go around that is you just take your sample, weigh it in your crucible, and then put it on a hot plate so you can burn off your fat. You can get rid of the smoke before you put it in the muffle furnace. Otherwise, if you just put it in the muffle furnace and the temperature goes up really high to 500, 550, the fat starts to burn, and by burning it might splatter. If there is and then by splattering, then you will lose sample as well. Other problems when problematic samples is plant material that is high in moisture. That's why drying is important. And meat is also high in moisture. So that's why, again, drying is important to avoid a spattering and swelling and sample coming out of your crucible. The products that's high in sugar will foam. So again, you need to do a preheating step, a gentle preheating step to start burning your sugar and avoid foaming. So the ashing methods, your standard method is dry ashing, basically. This is where you actually get a weight of the ash, and that's what you need to determine total ash. There is wet ashing, and this is where you use corrosive concentrated acids, and that is basically used for mineral determination, not for actual quantification of ash, because you don't get a weight of ash when you do wet ashing. You solubilize your mineral in acid, and that's it. You cannot get measurement. And there's microwave ashing to speed up the ashing process, and we'll talk about that too. So some of you have seen the muffle furnace when we put in your sample, except for one group that just left before we got to this step today, is you take your crucibles once you weigh out your samples and you put them in a muffle furnace, and that gets heated up to high temperatures, 500 to 550. You can get that temperature higher as well to get rid of your carbonic matter that are really hard to get rid of, so you can increase the temperature, but you have to be aware that you might volatilize some of the minerals. And so it's a simple procedure. You put your sample in, and usually overnight, and then the following day you turn off the muffle furnace, you wait a few hours until you cool down. You do not want to go in and get your samples out when it's too hot. It's really high temperature, so you just have to wait to cool, and then you take your samples out, put it in desiccator, wait to cool to room temperature, and you take your measurements. So crucible selection, there are a wide range of crucible selections you can pick from. The most common one is the porcelain, and that is basically what you use in the lab. It is not the most inert. That means it is not inert to alkaline, for example. If your sample is high in pH, that is not inert to that. Same with the quartz. It withstand high temperature, but it's inert to acid and halogens, but it's not inert to alkaline. But this is cheaper. It has similar characteristics, but cheaper. The disadvantage of it, if there is a temperature change that is very fast, it might crack. Platinum is the ideal. It's inert to everything. Inert to acid, inert to alkaline, inert to halogen. Can withstand really high temperature, but it's very, very expensive. So you don't usually see it in labs very often. Another cheap option is your steel, but that could cause contamination, mineral contamination to your sample. The last one you have here is quartz fiber. So this is quartz glass material, and this is quartz fiber. It's porous. It's disposable. It withstands high temperature, and it allows a good circulation of heat because it's porous. So the temperature change in the sample happens very fast because of the porous material. And it's pretty stable. So these are the options, but what you have seen in the lab is the porcelain, which is the most common one used in labs. So disadvantages and advantages. So with dry ashing, it is really lengthy. You have to wait overnight, about 24 hours more often, and not just that, you have to wait for the muffle furnace to cool down, and then take your sample out, and again wait until the sample is equilibrated to room temperature. So it can be lengthy, but it is little attention is needed. You just put your sample and leave, and you can analyze many samples at the same time. Disadvantage at the beginning, it's expensive equipment, but once you have it in the lab and you have it, it's just a one-time purchase. And another disadvantage is the loss of volatile minerals if you are after analyzing them. You have to be cautious on how to prepare their samples. So it is a safe method. No reagents or blanks are needed, so it's pretty straightforward. And like I said, little attention and many samples can be analyzed at once. What sources of error in dry ashing you can think of? So it's a simple procedure, but it is associated with few errors.
If you don't mix the sample in some sort of acid, I remember the functional groups from a glass of plastic container could.
No, that's what you're thinking about mineral analysis.
Oh,
We're talking about just sources of error for dry ashing. Go ahead, Ben.
If you don't burn off the organic compounds, then you can have overestimation.
That is one thing, yes. You can have overestimation if you don't completely burn off all your organic matters. So think along these lines. What else can happen? Yes, Joshua?
The cross on the contamination the lab equipment.
Contamination, if you use the mill, for example, and that mill is metallic, so it can get metallic form of elements into your sample. Yes, contamination. Yes, Josie?
If you use too low of a temperature, it might be incomplete.
Yes, that's what Ben said. When you do not combust all of your organic matter. Let's see what else is there. So we talked about microelement contamination and incomplete combustion. So there's also volatilization of elements. When you get, at this point, you get underestimation when that happens. And if your sample is high in moisture and you do not pre-dry and you put your sample in and this starts to boil off and splattering occur. And then, of course, this is typical for any type of analysis. If your sample is not representative, not homogeneous sample, you did not mill it appropriately, and you grabbed a portion of a sample that has not been homogenized. All right, let's grab a piece of paper, write your name on it, and let's do some +2 exercise. So it's time to solve some problems, and with these exercises you're going to practice how to convert from dry to wet, wet to dry, fat-free bases. A lot of these are important. And for example, when you do your project, you'll see that you need, on dry bases or fat-free bases, you need to have a certain solid content or certain protein content or certain ash content. So it's important to know how these calculations are made on fat-free, on moisture-free, on fat and dry bases. So give it a go. And whoever is ready first can let us know. So you have an idea? You're done? You got it. Okay, what did you do then, Eric?
So the equation is percent ash dry basis equals percent ash wet basis times 100 divided by 100 minus percent moisture.
Yes.
So I got 2.15.
Okay, I'm gonna write this down and simplify it so you guys can see the concept. So if you have total solids, I'm going to say, that's your solid matter, and you have your moisture. If we say percent, this is going to give you 100%, right? So percent total solids or dry matter. Do you want me to call it dry matter? Maybe it's better to call it dry matter. Percent dry matter plus percent moisture equal 100. Okay, so basically you have your ash on wet basis and you wanted to convert it to dry basis. So it's 1.14. That's your percent ash on wet basis. And then you want to multiply that by 100 because it's out of 100. Okay? And then you want to divide that by 100 minus your percent moisture. So this is your dry matter. So you have ash over dry matter times 100 because you really don't have this value. So you want to assume a percentage value. So you go, this is a percent, that's the total. This is the total minus moisture. This will give you percent dry matter. So percent ash over percent dry matter times 100 will give you percent ash on dry basis. Okay? So it's the amount of ash relative to the dry matter times 100. Are we all good in this regard? Okay. So this would be your answer. So you have your moisture is about 47%. So 100 over 100 minus 47 is 53. So you get the ash on dry basis. So to know that you've done the calculations correctly, you always, your percent of dry matter on dry basis is higher than percent on wet basis. Because here the denominator is lower than 100, right? So always when you are looking at a component with respect to dry matter, your value or your answer will be higher than when you are just looking at a percentage on complete or wet basis. Questions? Okay. Now here's a tricky one that requires multiple steps. What is the percent ash on fat-free basis? So this is a couple of steps calculations. What do I need to do first? The first step.
100 minus 47? Because if you're going on a
I didn't say dry basis, I said ash on fat-free basis. What is the given? What do you have? So fat-free basis, meaning, so you have your moisture, you have your percent fat, you have remaining dry matter because there's fat removed from that. I only want it on fat-free basis. not on a dry basis, on a fat-free basis. So I have the percentage fat on dry basis. First thing I need to convert percentage fat to wet basis. That's the first step that I would do. Because this is not on a dry basis, so I need to bring back the moisture. Okay, so how do I convert 56.6% fat to dry basis? From dry basis, sorry, to wet basis.
56.6 divided by 100.
In this case, your denominator is your 100, because that is your total. That's everything. Okay, so you want to get the percent fat. So you want to get the percent fat in here, but then here is where you have your moisture content. So it flips. So this is your total, and this is your original dry matter. So you multiply this by the dry matter over 100, you get your wet basis. So what is the wet basis of 56.6% fat?
30.
Huh? 30? Okay. Now I have 30% fat. So now I have 30% fat plus everything else equal 100%. So everything else equal 100 minus 30% fat is everything else. So I want to get my percent ASHE relative to everything else. So that would be percent ASHE over 100 minus 30%, that's my everything else, times 100, given that it's a percentage, then you'll get percent ASHE on only fat-free basis with moisture included in everything. Then you'll get that. Okay. Good. All right, so wet ashing. So it's mostly used for preparing your sample for mineral analysis. So wet ashing is basically involving corrosive acids that are highly concentrated. To oxidize, instead of burning it off, it's just digesting it with an acid and also oxidizing it into fumes, basically. So the combinations that are commonly used, the most effective combination is your nitric acid and perchloric acid. But perchloric acid requires, it's a very corrosive acid, requires a very special hood called perchloric acid hood, which is not always available in all labs. So what you would do in this case, you use a combination of sulfuric and nitric acid. It's still effective. You put your sample in a tube, basically a digestion tube. You see this here. There's a block that heats up and you have your tubes. You put your sample in there. You add a combination of sulfuric and nitric acid. You heat it up to 200 degrees under the hood because you'll start burning the sample and fumes will come out. The fumes are a combination of carbon dioxide, nitrogen oxide, sulfur dioxide, and H2O as well. So your sample starts turning black because it's burning now with the acid and heat. And then you'll see fumes start coming off until no more. When all the fumes comes off, and then your sample turns a kind of a straw yellow, a clear yellowish solution. And that's when you know that all your organic matter is oxidized, and what's remaining is your minerals solubilized in the highly concentrated acid. And with that, you have your starting solution for if you want to do atomic absorption or atomic emission spectroscopy. You have your minerals already solubilized in your acid solution. So disadvantages requires constant operator's attention. So you don't put your samples and leave. It's you're heating up acid and sample. You have to be around. Make sure that everything is going properly, working properly. You're working with corrosive reagents, so you have to take extra measures, and sometimes you need special hoods. And you cannot handle more than a small amount of samples at a time, or number of samples at a time. So if you see here, you have room for 6 samples in this block, whereas if you have a muffle furnace that is large enough, you can put up to 24 samples in the muffle furnace to ASHE. So you can only manage a few samples at a time. Advantages: samples are ready directly for mineral analysis. They are in solution. You don't risk volatilization of minerals because the temperature is low. It's about 200 compared to 500 degrees Celsius. And oxidation time is short, so you don't need 24 hours to ASHE your sample. Microwave ashing, while it's not yet an official method of analysis, but there have been reports comparing results of microwave ashing to regular dry ashing, and results are comparable. So it still gives you pretty good results. However, it's an expensive equipment, but once you have it in your lab, you can use it. And you can do microwave wet ashing or microwave dry ashing. They're 2 different instruments, not the same instrument for the 2 applications. It's very short. You reduce analysis time to 30 or 40 minutes. Even in some cases, it's 20 minutes. So it's really short analysis time. You operate under pressure. With that, the boiling point of your acid becomes higher, so the acid digestion becomes more efficient. So you don't evaporate the acid during digestion. And since you can raise up the temperature higher than the evaporation or boiling temperature of the acid under atmospheric pressure, you can use less corrosive acid and get effective results. You don't need perchloric acid. And you can do multiple samples at a time depending on the vessel of tubes you have. So here's an example here where you have a wheel where you can go up to probably 40 samples. And this is a closed vessel system where you can apply control pressure and control temperature in this. And analysis time is pretty short, about 30 to 40 minutes, like I said. There is the open vessel system where it's mostly used for when you want to ASHE a large amount of sample. And with that, it has its own exhaust system where fumes are sucked up into a compartment and neutralized. So it doesn't have to be under the hood. The dry ashing, it's also a microwave dry ashing furnace where you heat by microwave, and it can go up to 1000 degrees Celsius, the temperature. So it can go up to high temperature, and again, analysis time can be 20 minutes, 30 minutes, or 40 minutes, depending on the sample you're trying to combust. And it's pretty good, gives you very comparable results to regular muffle furnace. Okay, to that same piece of paper, try to answer these questions. Take a few minutes, 2 or 3 minutes, and then we'll answer them together. First of all, do we always listen to our boss? What does that mean? Do we always listen to our boss? No matter what, we just say yes? No. Right, girls?
They're not listening right now.
What's that?
They're not listening right now.
No, they're not. Do we always listen to our boss?
Yes.
Amy is a goody two-shoes, is that what it is?
I want to graduate.
Well, maybe you shouldn't listen to your boss if you want to graduate. Okay, so here's the poor employee trying to do the right thing and use dry ashing method. And here comes a boss, wants to save time and money, and tells you, no, wet ashing is faster. It takes less time. So do you agree or disagree concerning the time issue? Yeah.
It takes more time overall. Oh, sorry, it takes less time overall because the house is kind of shorter, but then you need someone to stand there and watch it for a few more employee time.
That is very good. Yes. So yeah, your boss was right. It's shorter in terms of total time, but it needs your attention. So instead of weighing your sample, which takes 5 minutes, and putting them in there, you will probably need 2 hours just out of your time that you could do something else, trying to analyze ash content. Okay, that's with respect to time purely. All right, what about the other thing, not considering the time issue? Why might you still want to continue using dry ashing? Yes, Agnes.
The number of samples in dry ashing is larger than wet ashing.
Well, that is correct, but if you want to determine percent total ash, would the wet ashing give you percent total ash? No. If you're after determining percent total ash, you cannot use wet ashing. It won't tell you percent ash. But if your purpose is for mineral analysis, then yeah, you can consider that, if that's more important than your time standing 2 hours working on a corrosive, highly involved method. So, did we capture everything? Time-wise, and the final what's your objective? What do you want to compute? Do you want to compute total ash, or you're just doing ashing to determine mineral? These are important factors. So if you are determining ash percent, you have 2 arguments to present to your boss. One is where can get percent total ash, which can end the argument right there. And the other is the time it takes to do the wet ashing in terms of your actual time doing the experiment. Moisture lab is done. Proximate analysis with ash, fat, and protein. We're in the middle of it this week. Just a reminder, this week is only ash and fat. Next week is protein. And there's nothing much to say. Yeah. Okay. We're right on time. Off you go. Or don't if you have quality.